Hello, everyone, and thanks for joining this session from bench to cloud. Um, I hope most of you had a good day since the morning. And I'm Ajay. I'm from Ireland. I've been with LabVIEW and National Instrument ecosystem for quite long, like 15 years now. And this topic specifically is going to discuss about how we manage to bring up a solution that required us to pass the data collected in the local benches to up in the cloud, not using gRPC but using the WebSockets and WebSockets IO. So I will probably give an idea about what happened, why we try to choose WebSocket over the gRPC, what we found, the differences, things like that. There was a presentation this morning from Value guys and even a few other guys talking specifically about the gRPC, remote procedure call from Google. And so this is essentially about sending as many data as you have collected as a data stream from your local bench to up in the uh, different application. It's a communication layer. So in this, we will explore about the WebSockets specifically. Right. So I thought of making it as more interactive. But if you find a mic to unmute yourself, feel free to unmute anytime and speak. I'll keep my eye at the chat, but if you have any questions at any point of time, just feel free to unmute and speak. I have only a little bit of slides. Probably I'll give the demonstration of how it happens in our side. Right. So I'll walk you through what is that we were trying to do. So we are trying to develop a calibration management system, which is a cloud solution, a SaaS solution, software as a service, and it can help the maintenance people basically in any environments where they are trying to manage various calibration systems. It could be the equipments or the small calipers or mechanical gauges. We try to bring up an application that allow them to have a dashboard view of how it for their day-to-day operations. Basically, the maintenance people, they might want to have a look at what is the current status of the calibration of all their equipments in the facility. Then probably help them to figure out if there is any alert they want to calibrate some equipment sooner for some production needs. They can use that as a platform to figure out what is important. This is what we were developing and for a couple of years now, and over the last almost a year, we were transitioning that into the automated system where if you if you are doing a calibration in-house, you can develop your own calibration solutions. For the sake of calibration, the calibration could be very niche from case to case. It varies, just like how we provide a bespoke lab applications. It is very bespoke, and each calibration might need its own the reference data, the UUT data, and analysis and result recording, things like that. So Given that each of them are very bespoke, we thought we can try to make it a generic framework, like API provision in our solution, and the customer can use these APIs, be it LabVIEW or Python or C Sharp, whatever it is. They can develop their own application and interface it, send the data to our SaaS solution. So I will provide a basic idea about what is that solution that we have, and then where we wanted a communication method to send the data from the local test benches or local agents that do the actual calibration and pass the result back to the cloud. We decided on a specific communication method, and why we went for the WebSocket specifically, and some architecture of how we did that. Basically, we used DQMH to keep it as simple as possible so that it is very accessible to anyone who is adapting to the LabVIEW framework. That's only on the LabVIEW application side. On the Python and C Sharp, it's a different approach. We don't have a DQMH there. DQMH is for LabVIEW platform, LabVIEW based design pattern, basically. So we'll explore a little bit about that. At any point, if you have any questions, do drop the chat there, and we'll have a look. A quick introduction. I think I tried to give an introduction already. A quick introduction about GageMuckle. GageMuckle is a SaaS solution, software as a service, that allows the calibration management of different equipments that you might encounter in any enterprise. Um, we addressed this for a bit large scale enterprise rather than a small scale enterprise, wherever the calibration is really a separate human activity. Um, and for example, in case of enterprise who has 100, 500 and plus or thousands of equipments that needs calibration on regular basis, in case of pharma industries or medtech industries, where calibration is very critical, and if the calibration is false behind, the whatever you produced will be called back from the customer. That's very serious thing in pharma and medtech industries. So that's where we targeted the whole solution is about. So when such a number of equipments are there, for example, in one of the industry, we found they have 20,000 different equipments just needs to be managed, and they have a better solution than just simply relying on an ERP solution like SAP, which also has a calibration component, or very simple solution like an Excel sheet, for example. That's definitely no go. So we try to find that space and try to help the calibrations of such a huge volume of equipments. And so we brought up a cloud-based solution for this. As SaaS is always a cloud-based, so it's a cloud-based solution. It has a different screens like dashboard and list of equipments and alert systems and email alerts and users and grouping of users, all those different typical SaaS solution components in it, addressing for this. Initially, it's just for management purposes we started off, and we had in our mind we need to automate the a subset of the calibration which is controllable and which can be done in a click of button. So all calibration is not a click of button, but many of the electrical and electronic calibrations could be a click of button. So such calibrations we wanted to automate. So that's where we started diving into the specific electrical equipments, like what you see here, some of the electrical equipments which could be automated using a program that could be written with LabVIEW or Python. So before I dive into that, I can show you this. A quick walkthrough. Some of the screens that we have, the a dashboard and a list of equipments, and this is the dashboard. What are the different alerts, this critical items that has come up, and list of equipments, and what is the specific equipment that needs alert, and the calibration process itself, the workflow of the calibrations on the website. All this on the website, web solution side. You could have a calibrator to calibrate it and then send it for an approver, who is typically a quality manager in such an environment. They need to approve the calibration certificate that comes from the calibrator, be it a local calibrator or an external calibrator. So the workflow for that, and some of the screens are a bit old. We still have to update the website. Basic idea is allow all these different stakeholders within the manufacturing facility to collaborate. For example, in some instances, we found they still used papers. They try to write it down in the papers and pass the papers, scan it, and pass it as a digital certificate. So that's still a collaboration on a paper level, but it could be done in a digital level. And the clustering of gauges, that's very specific for the calibration process itself. To do the calibration, you need a reference standard that can tell you in a high precision measurement. It is for whatever the measurement that you make, that it can say in a very high accuracy level, so that you know the UUT, the device under test that you're testing, is getting closer enough to whatever you're trying to measure. So for that, you might have a numerous UUTs. For example, you might have a 10 different DMMs, handheld DMMs in your facility, and you would try to calibrate that with some high precision agilent DMM. 8.5 digit DMM could be your reference standard, and all your handheld DMM could be hardly like 4.5 digit or maximum 5.5 digit, I would say. That's what you have it in a handheld. So 5.5 digit DMM can be calibrated using the 8.5 digit DMM. So that is, clustering, so these 10 different your handheld devices could be now clustered to refer to your the high precision device. So this is very niche, of course, for that specific application. The reference gauges and allowing the scheduling. Sometimes the reference gauges that I told about, 8.5 digit, has to go out to get calibrated itself first on a regular basis. If that is out of calibration, it might bias or deviate. Then whatever the measurement we make with the 8.5 digit might go wrong. So in that case, that has to go out. If the reference goes out, all your 10 different handheld DMMs has to wait for your reference to come back in. So there is an interlock there. So when this goes out, the system should be intelligent enough to tell the operator, the calibrator, okay, you better do it now, or you have to wait for another month when this go out and come back. So the system enables such an intelligent scheduling to allow the calibrator to advance it or postpone it as they want. So that's the intelligent scheduler. And usage counters, sometimes they calibrate based on the usages. If they used it for 100 days, they want to recalibrate it. So such a different features, we try to bring it in on the cloud level. Then over the period of time, this after these features are ready, we wanted to provide them with an automated solution. They can now connect their local bench to automate their calibration process. if they have it in the uh, local agent. So if you have any questions up until now, do give me a shout. Else I go into the technical aspect of that, how we did that in the calibration. Right. So even before, I think I can show you a quick view of how the dashboard looks like. Yeah, this is a typical SaaS application. So you usually have an app running on the cloud, and when you try to log in, it asks for the username and credentials to identify yourself. Here is a test application, test organization we have. So once you log in, you have this kind of different dashboards that tells different parameters for the calibrations and how it is distributed. Basic dashboard of that, and yeah, it can list various different equipments that you might have in your organization, and you can basically play around it. Like you can say that specific equipment, what is it? You can set some image and things like that, and you can add the details like what is the serial number and what make it is, like Agilent specific model. This is the serial number, and which calibration team is using it, and when is the next calibration due date for this specific equipments. And you can say whether you are going to do the calibration internally or externally. And this is where the thing comes very technical here for our reference. So if this specific equipment, let's say the Agilent, this model can be calibrated in the local bench, or you have it your own calibration laboratory bench, then you can put it on the specific agent. In this case, I have a local LabVIEW agent that can identify the that type of instruments, Agilent G model. It can run, you can calibrate on the bench. So you can connect your cloud application to this local agent, and you can say this is the type of the certificate for this agent, and it has to run through the different test points and get the calibration reference details. So that way you can give some more details about each different equipment, when it has to be calibrated, what is the frequency of the calibration, when you want the alerts, the calibration alerts for that specific equipment or list of equipments. And you might have a calibration history here if you have one. So that's the basic idea about the application itself. And here in this at a point, we have something called as agents. So agents are the LabVIEW applications in our scope of talk. What we have, the LabVIEW agents can connect to this and communicate the calibration results. So how it does it? It does through the WebSockets. So before going into the WebSockets, what we did is we try to use the gRPC, because everyone talks about gRPC. We don't know what is gRPC. We don't know what is WebSockets before doing this. We were basically trying to do things like when you try to trigger the calibration from that application. So you can see that we have a calibrate button for this equipment. So you can just trigger the calibration from here. What we wanted is it was a manual process. It is very typically a manual process, and this is a very niche set of people who want to automate it. And when they click the start calibration here, we wanted to send that event to the local agent, and the local agent can identify, okay, someone wants to calibrate this equipment, and the local agent can run a program. You can imagine a typical LabVIEW program. You can run a LabVIEW program, and then after running the program, it can pass the details, the results, whatever it has acquired from the reference instrument and the, the equipment you under test. It can bring and do some processing locally and put it back up to the cloud. So when you look at here, there are two things happening for the communication. We send the event from the web interface to the local agent, and the local agent does the job, and then while it is doing the job, it will keep populating in the UI. Okay, this is what the test point I measured. Next this, maybe in the waveform or in the UI in this web browser. So the event goes in, and the data comes back in a broadcast version. And once the event is finished, it has to finish the calibration, and it has to go to the further steps on the UI workflow. So we started with the gRPC. We tried to play around. Then we stumbled upon, like, okay, how we are going to capture the events now. So we have to poll for a REST API. Like, we have to poll for keep getting and doing the stuff, or is there a better way to do that? So then we ended up. To be frank, we jumped into the ChatGPT and Gemini. We consulted them. we said our problem, and we got an almost immediate solution. Like, okay, don't use the gRPC, go for the WebSockets. And in fact, it suggested all different methods of doing the communication, which we don't have it in LabVIEW. So we wanted to find something that we have in LabVIEW and we can achieve with LabVIEW, uh, but still it serves our purpose. So we can send the event and broadcast all the results back. I see some question there. Sri, do you also have a provisions to extract calibration factors and or factors from the cloud in order for the application to read those factors and apply those factors in the calculations, for example? Yes, we are doing that, Sri. So we can um, the procedure that I talked about in here, I can go back quickly for you. So we have the certificate reference that you can develop in the cloud that has all the test points, and it can bring in all the test points. When you trigger the calibration here, it can bring in all the test points down to the agent. Now agent knows these are all the different test point factors it has to calibrate. It runs based on that set of factors that it has. I hope that gives you an idea. So thanks. Socket. We found it from Gemini. In fact, to be frank, Gemini is really helpful for us. I think it has accelerated a lot in many scenarios. I don't know if any topic ran about AI and ChatGPT, things like that. But for us, this has helped us a lot. We could immediately spot. We could use the WebSocket because we found WebSocket written by Media Mongrel Sam Sharp a while ago, and there is also a secured protocol, secured library that he has written, which has helped us to make it more secure way, and it is based on WSS HTTPS secured protocol. Then we understood, like, okay, we have the API library, we can make use of it and try to figure it out. And that's how it all started. And the main difference we found is the Socket IO allowed us to communicate back and forth compared to gRPC. gRPC, we felt like it's for just streaming. If you have established the channel already, you just want to stream the data, gRPC is great. But if you want same protocol to do both, gRPC is not going to work. That's when we decided Socket.io is the good one to go. So a quick overview. RPC enables the synchronous communication, yes, but it has to be established and you synchronously stream the data. That's how it typically looked like for us. That's been used. So gRPC offers the high performance open source transport from Google. Everyone knows by now by this time. And WebSocket helped us in a full duplex fashion. We want to do it in both directions and capture the events. Specifically, the events it's built in the socket Socket.io. By the way, Socket.io is a framework over the WebSockets. And there are many frameworks over the WebSockets. Socket.io is specifically with the events and everything helps us to bridge that gap. Yeah. So why WebSockets? It's the it offered a persistent connection. So as I said, we wanted to keep updating the web application as we collect the data, so that user can know what is the current state, current test point being tested. So it can be lively seen, and they can also offer two-way communication events and reading back of the data. Before I go into the further details, probably I can show here how the LabVIEW application is working for us. I try to open up my virtual machine here. Oh, it's not a virtual machine, by the way. It's right. All right. So here is our LabVIEW application. It's it's a prototype application. It's not a real application. We have simulated an oven calibration in the local machine here. This oven calibration is you can imagine there is an oven in the local machine, and we are trying to collect some test points like oven has to be calibrated in 0 degrees, 10 degrees, 100 degrees, maybe 200 degrees, something like that. So when we trigger the calibrate button from the UI, it collects, sends the data, the test points to be calibrated, and the oven calibration runs locally, and then collect the data and send it back up to the cloud. So this application, before I go into the application, I can show the quick prototype for the socket IO that we have. I don't I don't think I can go into the details of it at this moment, but this is a prototype VI. You can see all the scrambles here. I can quickly show what's happening here. A simple producer consumer. I just established the WebSocket, and from the WebSocket, as I said, Socket IO is built on top of the WebSocket. WebSocket gives a layer of communications between two entities. And over that, the Socket IO allows you to do the regular connection, disconnection, identify the event that is being happening within that connection. So within a connection, it could be two entity, or you can create a room in Socket IO where you can have more than two entities. Uh, we are using that for the fact of local agent as one entity, your LabVIEW application. The backend server is another entity. So backend server can listen for the events or whatever is specific for the backend. And also the front end is another entity. If you open your browser tabs, multiple browser tabs, each of your browser tabs becomes an entity now. So your browser tabs will define each as an independent entity. It could be any number of entities, as many as you want. So when your local agent starts updating the data, uh, everyone in the room will be able to listen that, okay, this event is happening. So in the backend would listen for it and probably log it in the database. This event happened in this time. This test point has been acquired at this point of time. Put it in the database in the backend side. In the front end, you might have a graph. Graph can represent what is the recently recorded data, or even you might have a simple console log that is another entity that tells what is the communication happening within these entities at the moment. So you have the event from the socket IO, and then error error information of the channel. If any error happens within that channel, you can immediately have an idea what went wrong from the very top level. And we didn't use much of the other stuffs, in fact, to be honest. So we used connect, disconnect, error, and event. And the binary event and binary acknowledgement, we haven't used it yet. The acknowledgement wise, the framework itself manages that. It sends event from one entity to the room or other entity, and it can acknowledge itself whether it has received on the other ends. So we were fine with that. EIO is the layer in between the WebSocket. There is a WebSocket, there is an EIO, and then the socket IO. So essentially, you need to open the EIO first, and then go into the socket IO. The EIO does the liveliness. It has the ping pong between them. So once any of your agent gets connected, um, any of your entities gets connected, they have to keep pinging their presence. If any of them doesn't ping for a defined timeout period, and that's typically like 25 seconds or something, for 25 seconds, if some entity failed to ping, and in that case the other entity decides, okay, line is lost, it will automatically disconnect itself. That's great. We don't need to manage all of those things. It's all built into this same framework, the entity IO and then socket IO. So we felt like, okay, a lot of our job is done here, we don't need to worry about too many things. uh, for it, I probably give you a ping pong here. Yeah, here is the ping pong. So whenever the socket gets established, soon after we look for the number two. Basically, is the ping from the other people on the network. So if there is a ping, we try to pong it. So we send a three here, which is a pong. So the ping pong should happen at least once in every 25 seconds, but it's happening. It's just waiting for like some time, and whenever it finds it, it pongs it. If there is no pong, the ping is coming from the other entity. If it will try to ping, if there is no pong from you, it will decide you are disconnected. So we do that here in the EIO level, and on the socket IO level, we do the events. So we send the events like a new message from the LabVIEW agent, and that goes to everyone in the room. So there is some defined for two, that is basically the definition of I think message. Four stands for message. On the EIO level, we say it's message, and then we send two. Two is basically the event 0, 1, 2. So we send it like, okay, this is the 42. We are trying to send a message through the WebSocket through as event, and then we send some payload for that. When we send that, the other one will understand based on our details. Like we say that what is the event name and what is the payload. So based on the event name, we would have defined on the server side, the backend side, okay, for this event, let's say an event has come from specific agent. So if this event happens, we have to log that event and probably show it in the UI. So we just like an function name, we define it as an event name, and then do the respective actions based on that. If you have any questions, do throw me at the chat. And so some of the debugging screenshots and other stuffs. But here is a quick sequence diagram between the entities here. So we have a web UI, a cloud, which is a backend server, and the agent. For example, the agent can connect first and tell the cloud, I'm ready now. And once the cloud finds that it's ready, the cloud will enable the UI to allow the start calibrations. So when you trigger the start calibration, again, cloud will listen for that event. And then if that event is specifically like start calibration, for example, then if it is start calibration, it will tell back to the agent like, okay, now start the calibration. So now the event comes from the backend to the agent. Okay, I have to start the calibration. Your LabVIEW application basically listens, waits for this. Once it has found that event has arrived, it will do the start doing the calibrations. That's it. Back and forth, the event exchanges, the results and test points and errors, whatever the be it, it gets exchanged between them through this way of a simple sequence architecture. So that's a prototype I try to bring up in this session, so that everyone can have an idea, a taste of how it is done. When it comes to a real application, what we did is we simply used a DQMH on top of the WebSockets. So here is oven calibration that uses the DQMH, and we have some modules, just a couple of modules for this simulated example. We have a gauge mechanical communication module that communicates to our cloud solution, and we have the configuration module and our test application itself, where the application is the where all the calibration logic goes in. In the backend, it's simply all different events that we capture. So whenever you try to start this will immediately send to the gauge muckle that you are connected, and it will send a welcome message, for example, and everyone knows you're there, you're connected. And then it will listen for the events in the gauge muckle communications module. Probably I'm going too fast here, because if any of you want to know, do stop me. And so in the gauge muckle side, it will wait for the listener, message listener. Um, so in the timeout, we look for specific messages, and all these are different messages like start calibration, instrument details from server. Instrument details is where the test points and other factors comes in, as Sri asked there. And there is a pre-verification, post-verification. Before really calibrating anything, you do a pre-verification. If everything is within the tolerance limit, you don't worry too much about. So it starts with a pre-verification. The server sends a message to do the pre-verification. So when the pre-verification comes in, the message comes in, the DKMH module will send a message to the main application, do the pre-verification. It will do the pre-verification and sends back the results. If the pre-verification fails, that means it's not within the tolerance. The equipment might have drifted or chain biased or whatever it is, and then it has to be calibrated by the time. So the server decides then, okay, do the calibration. If it is an internal calibration, that could be done in that bench. It will ask to do the calibration. If it is an external calibration, it will just simply ask to finish the calibration, and it will tell the user in the UI, okay, it failed. Now send this for the external vendor, whoever does the calibration. It just informs the calibrator in the front end. So it decides based on this. So server is the decision manager here. It decides what step to execute. The LabVIEW agent is essentially getting the different messages and just acting on the messages, what it has to do. If something can be done in locally, the server will tell, okay, do the calibration locally, and after the calibration done, again it will do the post verification. It will ask to do the post verification. So the message comes in back. You can see that the message, the events happens front and back here, and that's where the WebSocket essentially helped us. um, I can quickly run this application for you guys, and you can get a quick taste of it. So as I said, we have the agents here, and we have many agents. One of the agents that I have connected to that LabVIEW application is this Oven Cal agent 2. So it is right now, it is offline. It is listening for that agent to come online basically here. Whenever you have this application open, even the backend server is looking for it. So when this application runs, as soon as it runs, it communicates to the server that it's ready for the calibration. So when we go back to the UI, and probably we need to refresh it once to see it has come back online. It has come back live now. So it is ready for calibration. So now when I go to that specific agent here, oven calibration, hybridization oven, which is basically going to run the calibration here in this agent 2. When I do the calibration, now in this start calibration position, I have an information that the agent is ready, alive now. When I trigger the calibration, so this is going to start the calibration here. So I'll try to keep it in side by side to have a look. So, yeah. So when I start the calibration, you can see from the server, it just triggered it, and the local agent is running this now. It is doing the different step operations. Then once it has finished the calibration, it has moved the step from start calibration, pre-verification passed. So no need of calibration. It just uploads the current certificate that it has found and gives the link back here in case if you want to open. But essentially the link goes to this position. So now it has collected the information here, and the certificate is here. So the certificate probably looks something like this, and that tells what are the different test points, like low temperature, high temperature the agent tried to run. Since it is simulated, it's very fast in a snap of second, but in a real case it could be like 5 minutes or hours of time it will take to communicate. Um, so the agent has to be live all the way during the calibration process. Um, so this is how the certificate gets generated, and it could be passed on from this point to whoever has to approve this. For example, it could be assigned to a specific approver, a workflow process. Then it can be sent to that specific person. So now it goes to that specific person. They will get a reminder email. They got a new certificate. They need to approve it. Things, the stuffs like that, right? I didn't expect I will run through so many details. We are already nearly to the end of the session. Um, so that's a quick overview about how this agent works. The WebSocket helped us in LabVIEW. I'll just finish up some of the slides here. So that's the LabVIEW application. We try to integrate the cloud solution with the local solutions, and there is a real-time data flow now. You saw that as it was running that. Actually, I didn't show it up. Sorry about that. As it runs, that you would see the what is the result came back from the local agent to the cloud. You can see that gets populated. But we saw that in the final certificate, though. It show all the low temperature, high temperature, and everything. Um, if you have any questions, do shout at me, or I'll just jump to the quick key insights. This socket IO over the EIO over the WebSockets really helped us to fast track our activity. We found most of the things are already in place in the library in the framework, like opening, closing, who connected, who lost the connection, what is the event, how the event is passed as a message. All those things are put together in a package. We just straight away use it. All we wanted to do is we have to figure out where it is, how to do that. We don't want to spend too much time on debugging and figuring out connecting the elements there. So the in the future direction, we are improving the user experiences, quite a quite good amount of increase in the user efficiencies, user experience. um, Still we have the optimization, some of the performance challenges that we are trying to improve, but it's more about how our infrastructure is ready. We were able to bring in the secured the cyber security items, like is it secured, is the data lost in some way, like all those things, or the risk is reduced now. It has the HTTPS, WSS, WebSocket secure, HTTP secure items, and it goes for specific in specific organization, specific user. It has all the security activities around it. We are expanding on the performance items based on that at the moment. Right. So that's about it. Um, If you have any questions, I am open for your questions. I think I really brought in too many details. I thought it would be very quick presentation, like 10 or 15 minutes, but it went really long. Thanks, Eric. Thanks, Aaron. Um, Thanks, then. Thanks for all of your time. And if you have any questions, feel free to reach out to me. I'm open in this email, ajay@makkal.co, and we are exploring further on this. Thanks, Jessica. Thanks, Theodore. Right. Hope it has helped everyone. Thanks, everyone. Enjoy the rest of day. See you soon.